class. Welcome to the class this morning. And today we are going to talk about oxygen-dissociation curve. And we'll deliberately go slow so that we have enough time to process that we learned today. And feel free to interrupt me anytime you feel like. So ask me questions if you have any time. Don't put it until the end. Well, so what are we going to learn today? So we are going to learn about hemoglobin and the oxygen dissociation curve. And further we are going to learn about how the curve can change, how can it go, in what situation it goes to the right, and what situation it goes to the left, and what are the implications. And also we'll try to understand real life scenarios where the mechanism of oxygen dissociation curve comes into play. Let's talk about the hemoglobin. As you can see in the picture, hemoglobin is a complicated structure. Hemoglobin runs in our blood attached to red blood cells. Hemoglobin has, as you can see, I hope you can see, has 2 alpha and 2 beta chains. Beta chains and 2 alpha chains. In each of the chains, out of 4, in each of them, they have a heme group attached to them, which has a ferrous ion that picks up the oxygen in the lungs. So what is the function of hemoglobin? The function of the hemoglobin is to pick up oxygen in the lungs, and as they distribute in the circulation throughout the body, is to release the oxygen in the respiring tissues, in the peripheral tissues. With that knowledge, let's go to what is the oxygen hemoglobin dissociation curve. For a particular partial pressure of the oxygen, the saturation of hemoglobin, oxygen saturation of the hemoglobin is different. When it is 100%, 100 mm of Hg, that is mercury, it is 97.5. When it is 10, it is 13.5. It is the saturation of the oxygen in the hemoglobin in our blood. So when we plot these values, and there are different values in between, so when we plot these values with the oxygen partial pressure of the oxygen in the x-axis and the percentage of hemoglobin saturation with the oxygen in the y-axis, you get a curve. And this is sigmoid shaped curve. Why it is sigmoid shaped curve? Because as I told you before, hemoglobin has 2 alpha and beta subunits. So initially it is difficult for the oxygen to get attached to one of the heme group, but as soon as one of them bind, it is easier for the other chains to bind with the oxygen. That interaction is called allosteric interaction, or interaction of cooperativity, where initially it is difficult to bind, but once it is bind, it is easier for all oxygen molecules to get attached. So that's called the allosteric interaction. And as they bind the oxygen molecules, the shape of the molecule changes. As the shape of the molecule changes, and as it is easier for the other molecules to get attached, the shape gets changed, and it gives a sigmoid shape curve. So if we see at certain level, after like around 100, after that the curve gets almost plateaued. So no matter how much oxygen you give after that, the binding or the saturation does not increase. But if you look at this point, where the strip increase, where a small increase or decrease has a significant effect on the binding or the delivery of the oxygen. So this is steep curve where all the important thing happens in a way that there is a big change. If a small change in the pressure, there's a big drop or increase in the saturation of the oxygen. Okay, now comes the Bohr effect. What happens in the Bohr effect? Imagine our body is not uniform in the sense that the level of oxygen and carbon dioxide is different in different parts of the body. In the lungs, we have more of oxygen and less of carbon dioxide. In the peripheral tissue, we have more of carbon dioxide and less of oxygen. So, as you can see in the graph and as in the text, high carbon dioxide in the tissues causes release of oxygen from the hemoglobin. It's because when the carbon dioxide increases, the oxygens are bound loosely, and then they are easy to be released in the peripheral tissue. But in lungs, where carbon dioxide is low, it causes the absorption of the oxygen. So, what are all the things that can happen in muscles other than high carbon dioxide? It has high temperature. When you do a workout, it has high temperature. Since it has high carbon dioxide, the pH of it is going to go down. So all these things, low pH, high carbon dioxide, high temperature, all of these causes the graph to shift on the right. And all the opposite of that, low carbon dioxide, high pH, low temperature, all of these cause the graph to go on the left. So, now let's take some examples. If you look at the graph, there are two. One is in the black and one is in the blue. So the black plot is for the lowland animals. That's a typical normal oxygen dissociation curve. But llamas, which are South American horse, I guess, right? who live they live in mountains where the level of oxygen is low. And as expected, their curve is on the left. So can you tell me why? So far, what we have learned from what I had taught you, can you guys tell me why the oxygen dissociation curve for the llamas are on the left? Anyone?
There's lower oxygen in the mountains, so they need to pick it up at lower levels.
Exactly. Yeah, exactly. So even with the low oxygen level in the high mountains, they can actually have a good amount of saturation in their blood. But if you go and look at what happens in the 40s for the lowland animals and what happens in the 40s for the llamas, look at for the 40s, for the lowland animals, if the saturation is 70, for the same 40 mm of Ag, the concentration for the llamas would be around 90. So even with the low level of oxygen in the atmosphere, they can have a good concentration in their blood. And if you see on the right, so the most left graph is for the normal hemoglobin, and to the left are fetal hemoglobin and monohemoglobin. Again, this is very important because fetal needs more oxygen. They need to grab more oxygen. So what happens is they have a more affinity in the oxygen. So when in the placenta, when the blood is coming in, they can grab more oxygen, and that is physiologically advantageous for them. Same with the myoglobin. Myoglobin are there found in the muscles, as the name says, and they are the oxygen storage. And they hold the oxygen, and they don't release it until it's really, really low. The oxygen, the partial pressure is really, really low, and they release it at that moment only. So basically, myoglobin are the oxygen storage side in a way. With that knowledge, now I'd like you to discuss among yourself what happens in the altitude. When you and me go to the high altitude, what will happen? Please discuss among yourself and let me know what you come up with your answer.
Oh, I was just saying, you likely get a shift to the right in case of oxygen.
We do, and all the consequences of it. So
Right.
based on what we've got here, if I have less oxygen, oxygen is needed in those environments, and I will thus, basically I've got too much carbon dioxide, the
Yep.
pH of my blood's all messed up. And I'm going to start showing signs that my curve has been shifted to, well, my curve didn't move, but my supply did, to the right.
Oh.
But yeah, I was supposed to. But all those changes that will happen as a result may result in moving the curve. If my body's gonna try and compensate to move that curve, it would try to move it left with all of its systems it's got.
But then there's 2, 3 diphosphorylglycerate or
Yeah, BPG is
bisphosphorylglycerate
the
or whatever you're gonna call it,
Mhm.
whether you're a biochemist or a physiologist.
Yeah.
2, 3 BPG.
And BPG does that too. Yeah. And so do hydrogen ions for pH in its own right.
You get a headache, I don't know.
Yes, from the swelling and everything that result from.
You don't get like.
You can faint.
consciousness, yeah.
You do, from the swelling. Which
You also
happens,
have cognitive impairments too.
yes, definitely. It's kind of like mounting.
Yeah.
It comes from the swelling that is a result of the change in pH and CO2, things like that come from it. And the only way to fix it is to get down once it happened, like giving air isn't necessarily going to help, because once the system gets out of control, it needs to
Okay.
be pushed again.
Now you guys can come back and let me know what you have found. So what do you think? Anyone can volunteer.
So we think there'd be kind of a shift in the curve, we'd kind of see a shift to the right, and it'd make it more difficult for the hemoglobin to actually grab that oxygen to deliver it to tissue.
Right, and I heard some of you talking about 2, 3 BPZ. Yes, that's what happens because in the high altitude, they have to depend on the glycolysis, which results in the increased 2, 3 BPZ, and which simply grab to the right, and they have the difficulty extracting the oxygen. Okay, so what would be the solution? Or how they acclimatize? Look, eventually they will acclimatize, right? So what happens? How they acclimatize? What could be like possible mechanism to counteract whatever happens?
Once you've already got this, acclimatizing is not an option. But if you're going to avoid it, the best thing you can do is hang out at an altitude for a long time that asks your body to compensate for the shift in the curve by trying to shift it back the other way by making more red blood cells, physically more hemoglobin.
That's right. So as we acclimatize, what happens is we make more red blood cells, and that's how we are going to pick up more oxygen.
Altitude training.
Exactly. And you must have known about Serpods. Serpods who climb Mount Everest.
Oh, yeah.
And I happen to be from Nepal, where the Mount Everest is. So I know more about Serpods. And actually, when people look at what Serpods actually have, actually their graph is already shifted on the left. That's how they survive living there for chronic hypoxia for their lifelong. So the curve is already shifted to the left. That's how they survive.
So they're like llamas.
Exactly, yeah, like
Well, and, yeah, they go up
That's-
there and they don't need oxygen.
yeah, that's how they are done. They can climb the Mount Everest without oxygen. Sometimes they do.
Something like 40% more of a hematocrit total than most land lover things.
Like a story of a climber that he had like double the amount of oxygen capacity.
Well, and the funny part is, it only takes about a
The
month
guy
and a half to do that.
He did like Everest without the tanks or something like that.
And if you're willing to sit at base camp for a month and then at Camp 1 for 4 weeks, you can be just like the Sherpas, but people don't wait, and that's why
Yeah.
they die.
And every time I tell people to people that I'm from Nepal and where the Mount Everest is, people, the next question will be, have you climbed Mount Everest? I said, no. But I hope I'll do something, at least to go to the base camp,
Mhm.
which I haven't been yet, so, yeah.
That's okay, there's a lot of people that are not doing much.
Like, I always tell them, like, it's something like saying if you have a river on your neighborhood, it seems like everybody should know how to swim,
Mhm.
but they don't. So it's same like that. Mount Everest doesn't mean I have to climb it, or I know how to climb it. Yeah, with that, if you have any questions, I'm happy to answer that. Otherwise, we are done for today. Thanks.